Hi everyone. Welcome to Bitcoin Tech Optech sessions. Here we do Deepdive. Say this week we are having a look at newsletter number 356. So I have picked like four items from the newsletter, which will go in detail and try to understand the news item and the larger context around it. So the first one is about latency and privacy in Lightning. So Lightning, even though Lightning is a very is inherently a privacy preserving layer 2 solution on top of Bitcoin. There are some edge cases or attack vectors that can be used to de-anonymize or reduce the sender and receiver's privacy. So, so we'll have a look at how this how this de-anonymization can be done in order to like identify the sender and receiver's identities in the Lightning network. So we'll first have a brief look at what hash time lock contracts are. So as you all know, hash time lock contracts are digital escrows. So you put funds in and lock it using a time lock and a hash. So you can take the funds out of this contract only either if you provide the right hash or if there is an elapse in time. So this is the basic mechanism through which Lightning channels operate. So in this example, you have Alice, Bob, and Carol. So Alice wants to send funds to Carol via Bob. In order to prevent Bob from running away or cheating Alice with the funds, Alice enters or makes a hash time lock contract with Bob. Bob can claim the funds only if he can provide the valid hash, and the valid hash that Bob needs to provide is available with Carol. So Carol will provide the required hash to Bob only if Carol receives the fund. So by this way, during a successful or happy path, Alice sends her funds to Bob. Bob sends it to Carol, and Carol gives the hash back to Bob. And Bob uses this hash to unlock this transaction and collect his sats and some extra fees. So this is the happy path. During a conflict or during a disagreement, Alice can always recover the funds after a certain elapsed time, provided Bob doesn't provide the proper hash. So this is the basic of a hash time lock contract. So inside this contract, a series of message flows happen between Alice and Bob. This is how they obtain the hash time lock contract and maintain it and update it. So this is a small overflow or overview of the message flows. Alice typically sends an add HTLC message. He also sends the signed commitment to Bob. Bob can acknowledge it and send a message back, and also send the signed commitment back. Similarly, when the HTLC is fulfilled, Bob can send a update fulfill HTLC message. If there is any issue and Bob doesn't have, or like the the HTLC contract between Alice and Bob fails, this update fulfill HTLC is replaced with an update fail HTLC. So now we'll have to look at these three messages because using this messages, there can be an adversary can unravel or reduce the privacy between the sender and the receiver. So basically, typically the first message would be an update add HTLC message. So that's when the sender sends it and sends the information to Bob. When the final recipient, that is Bob, learns the pre-image, it sends Bob sends the update or fulfill HTLC. In case there is any issue or failure, that is, if Bob cannot forward it, then he sends a fail HTLC message back to Alice. So, how does timing attack use these message exchanges? So, there are two conditions. One in which the adversary sits inside the path, like there is an adversary between Alice and Bob, or the advisory can also be off path. So he doesn't have to be a active router of the Lightning channel. He doesn't have to be a participant in the routing. He can just observe the network and also perform this attack. So what does an on-path adversary do? He typically probes the entire network for latencies of target nodes. So how does he do that? He pings different Lightning nodes that are active and measures the time it takes for him to receive a reply back. So he generally gets an overlay of the latency in the entire network. So he can use this data to further de-anonymize the sender or receiver. So what does he do? He typically routes a low fee, low expiry HTLCs to collect these timing samples. So when he does that, there will generally be an exchange of messages in this fashion. So there will be an update at HTLC, and there will be an update fail HTLC. Because he is using a low fee, he is using a low fee and a low expiry HTLC, the chances of it failing are high. So he might get an update fail HTLC or update fulfill HTLC message if routing is successful. So what does he do is that he measures the time between the update add HTLC and the update fulfill or update fail HTLC message. So this can give him an estimate of the hop count, and he can pinpoint the sender or recipient based upon his idea of the whole network's topology. So he can also exploit the sender's retry behavior. Whenever a sender tries to route a payment and it fails, he will again try to resend the payment. So these are all default values that are encoded in node implementations, and unless and until you manually modify it, these are all default values. So based upon an attacker, based upon a sender retrying retrying to send the failed payment, he can sort of estimate or roughly place where the sender is among all the connections that he has. So basically, he computes the time taken between the retrying and the failing of the routing transaction. So this probably gives twice the time for the network, for the message or the HTLC to go between him and the actual sender. So so now he has some idea about the time interval. So now what he does is that because he has probed and measured the latencies of all different nodes that are already in the network, he can match this latency that he gets with the node that he wants to de-anonymize. He can match it against his database, and he can identify nodes that correspond to the network distance. So that's how he can get an idea of whether the node is probably within a certain geographical limit or it's very far away. He can make inferences based on this delta that he calculated. So this is an on-path advisory. Off-path advisories, they use ICMP pings, their protocol pings, network level protocol pings, to estimate node latencies. So they can observe the HLC messages that traverse through the network, at different vantage points and timestamps, and through this they can infer which node sits where. So they can sort of construct partial paths by matching incoming and outgoing HTLC messages within an estimated latency window. So they can, having collected all these data, they can do a search or the payment amount and the path constraints to narrow down the sender or receiver. So if you have look at the two methods, on-path adversaries are typically more effective in de-anonymizing the sender or the receiver than off-path adversaries. But being an on-path advisory means you are also committing to the network, and you'll have to put some money on the table in order to gain good network, good connection within the Lightning network. So how do we like prevent these timing attacks? At the node level, you can whenever you are forwarding an HTLC, you can add a small random delay for each hop. And if the delay is at least as long as the normal processing time of one hop, the attacker's latency estimate will be off. So that means like now you are not using the node's default settings while forwarding or relaying HTLCs. This sort of confuses the estimation that the attacker is trying to build, or the profiling that the attacker is trying to build. Then the other way is that you let the receiver wait a random amount of time before sending the update fulfill HTLC. So here, when you're so all these things happen sequentially over time, and these messages are the time at which these messages are sent out is hard coded into your node settings. So you can add a random delay. So once you receive a revoke acknowledgement from Alice, instead of relaying back this update fulfill HTLC after a standard time, you can add some random delay here so that this update fulfill HTLC goes out at some other time. So what this does is that it messes up the delta calculation that the attacker on-chain attack or the on-path adversary does by calculating the difference between this message and this message. So this is another way in which you can sort of confuse confuse the attacker. Also, you can encourage the sender to wait for a random cooldown time before retrying. So whenever a sender sends a message and tries to send a HTLC across and it fails, then he immediately tries to rebroadcast the HTLC through a different path. So if we can add some random time delay between this between the event of the sender receiving like the event of the sender knowing that his HTLC has failed, and he tries to rebroadcast. So you try to add a random time delay between these two. So in that case, this update HTML, so that will also like try to confuse the or try to pollute the assertion graphs that the attacker will be building. You can also do multi-part payments, so that is always best for privacy purposes. You split the X amount of sats that you want to send across into multiple payments, and you route it through different channels to the receiver. On top of it, if you add all other techniques that we have discussed above, it would definitely pollute or reduce the confidence in the attacker's methods.
Yeah, thanks, Bala. This was
so that is one thing, and yeah.
One quick question.
Yeah.
I'm just curious that like a very basic question. Why would someone want to do this? This is to de-anonymize and shrink the anonymity set, right? And this is specific to Lightning Network. So anybody who's on the Lightning Network will be an on-path adversary, and anybody who's off-path, it's easier to do that, right? I'm supposing that's the reason that there is a distinction between on-path and off-path adversary, right?
Yeah, on-path adversaries are much more effective than off-path adversaries, because off-path adversaries can only observe the network. They cannot observe the time that takes between a sender sending an HTLC and the sender receiving a failure message, and then he rebroadcasting the message. So these things an off-path adversary cannot observe. Only an
Right.
on-path adversary can observe.
Makes sense. Makes sense. Thanks.
Yeah. Yeah. So these are all recent observations by Carla of Chain Code Lab. So she has made some studies or research around this, and she has arrived at these potential attack vectors. And she is also providing a set of solutions that can be implemented into the protocol. So once it's implemented into the protocol, different Lightning nodes will try to implement it in their clients.
Wow. Okay. And is it a pressing problem? Would you have any idea that are there
Um,
people who have been doxxed because of running a Lightning node? Is that the reason that this?
so no, these are all at present only theoretical observations. There have not been any significant or known cases of de-anonymization happening.
Got it. Got it.
Yeah. Okay. So we'll, if there are any questions, I'll wait. Otherwise, we'll move to the next item. Cool. This next one is a bit interesting, and given the current context of core versus knots. So we'll basically have a look at what are all the methods available to store data into the Bitcoin blockchain. We'll also see why some protocols prefer to store their data using op return versus inscriptions. So that's what the whole debate is all about right now. Uh, yeah. So, because of Bitcoin's security and the block's stability, there has always been demand or interest in putting arbitrary data into the blockchain. This is not something new. It has been there since the very first Genesis block. Satoshi himself encoded a newspaper headline into the Coinbase data field. So, if you want to look at it that way, right from the Genesis block, arbitrary data has been put into the blockchain. So there are 8 different ways in which you can insert data into the blockchain. So this is pre-SegWit. Like these methods have been available since even before 2017 SegWit upgrade, and after the taproot upgrade, many more methods have also been possible to insert data into Bitcoin. So whatever we are seeing today are strictly pre-SegWit methods of inserting data into Bitcoin. So even now these methods exist, and you can people are using these methods to push data into the blockchain. So yeah, first one is Coinbase. So everyone know that Coinbase has a data field. Coinbase has a data field inside it, and you can use it to store arbitrary data. So here is the Coinbase data field. This is a normal transaction. This is a Coinbase transaction. So inside a Coinbase transaction, there is a data field. You can store arbitrary data into it. You can store up to 100 bytes of data into the Coinbase data field. So this has been there since the inception of Bitcoin, and this has been used by Satoshi himself. The only problem is this data field is available only to miners, and only miners can put in data into this field. Miners have been using this field to typically insert their name or the pool's name into it. So that's how the Coinbase transaction has been used to store data. Because it is used only by the miners, it's not that popular, and miners don't have much incentive to store data in it. You can always like pay a miner um, to store your arbitrary data in the Coinbase field. But we don't know somebody has done it or not. So that is always a possibility. So that is the first way in which you can store data in Bitcoin. The second way is to create a
Quick question, Pankaj. Okay.
yeah.
And let me know in case you want the questions later. But I'm just curious that you mentioned that if someone wants to potentially have a transaction with arbitrary data in the Coinbase output, they can pay the miner to do that, right? And uh, that will be off chain, right? Because the Coinbase transaction is the miner creating the transaction and rewarding the output to themselves, right? So somebody has
Yeah.
to pay them off chain, right? Is what I'm imagining.
Yeah. You have to contact the miner and say him that you will pay so much, and you ask him to put this transaction on this block.
Yes. Got it.
Yeah. Okay. The second one is pay to fake public key. These are all legacy stuffs. Nobody uses them now. So a typical script pub key of a pay to public key goes like this. So you have a public key, 64-bit public key followed by object 6. So this is the earliest script pub key that were used, where you directly put the public key in your script pub key. So here, what you can do is that you can replace the 65 byte data public key with some random data that you want to store. So what happens is that this typically burns your Bitcoin, which means whatever amount you are locking with this script pub key can never be spent, because you are not putting a public key which has a corresponding private key here. You are putting some random data, and that random data will not have a private key. So this is how people were using using transactions to store data. Uh, uh, to the ping of and no easily filter that as the was quick over the course of development of Bitcoin. Now nobody uses this for either transactions or for data. This method was there. Okay. The third one is pay to fake key hash. So after after the pay to public key, the pay to public key hash type of script evolved, and this is typically the standard script that is used to lock your Bitcoin. So you have this standard script, and here you have a 20 byte hash of your public key. So in this type, you can replace this 20 byte public key hash with some arbitrary data that you want to store in the blockchain. For this also, you must spend some value of Bitcoin that is above the dust limit. Otherwise, transaction are less likely to be mined. And whatever sats that you put into this transaction typically gets burnt, or you cannot you cannot spend it again. There is no private key corresponding to this public key hash. This method also contributes to the bloating of the UTXO set. But this was like very famous, or people kept using this for some time because it is hard to detect. Because whatever 20 byte hash you put in here, nobody knows whether this hash corresponds to a public key or not. Only the creator of the transaction knows it. So there is no standardness rule that can help you detect this kind of data storage operations. The problem is it's very costly because you have to burn some sats, and also the amount of data that you can store is quite limited. But people have used this method to store JPEGs and stuffs from time immemorial. So
I think, and correct me if I'm wrong, those JPEGs are just hashes on the blockchain, right? So it's not a concern from the data storage spam protection lens, right? Does that make sense?
They are all hashes, but the issue, but the issue is in this method you have to spend some sats to this address. Okay,
Right.
so for this script you will get an address, and you will have to put in a sat limit which is above the dust relay limit. So that means that sat gets converted into an UTXO. So you finally get an UTXO, and that UTXO is unspendable further.
Right. Right. Right.
So
Yes.
and also it appears as a standard P2FKH transaction, and nobody knows whether it's a data carrier transaction, or it's somebody has a corresponding private key to this public key hash. So nobody knows. So these are all sits in the UTXO set, and they bloat your nodes. They hog your nodes memory.
Makes sense, makes sense. And I think this could be tangential, but I'll just mention this. Maybe we can discuss this after the session. I think the bloating of UTXO set is a bigger problem than any spam technique, right? Whether that's op return, whether that's inscriptions, runes, whatever. Because bloating of UTXO set, like you said, is possible with pay to fake public key hash and other techniques, right? Which are legacy methods, which are way before SegWit was even introduced. And it's a long-term problem, right? Because in 2055, the potential UTXO set could be massive GBs, and for individuals to still be able to run will be a concern, regardless of op return drama, regardless of inscriptions.
Yes. So that is a problem that is a core problem why people are very passionate about this. So we have to find some way to rationalize the UTXO set. Yeah. So a rough of the back of the envelope calculation, if we do in one single transaction, like there is a standardness limit for Bitcoin cores. So you have 100 KB as the limit for a transaction. So if your transaction size exceeds 100 KB, so it is considered as non-standard, and your core won't relay it. So if you take 100 KB as a limit, you can store up to like somewhere around 3000 bytes, or approximately 3000 bytes of data, using this method in one single transaction. So this method has been the most popular method, and many protocols or many data storing services have exploited this in the past, but because of their costly nature and the need to spend some sats, they have fallen out of fashion these days. Okay, then the I don't know which one, two, three, fourth one. Okay, the fourth one is a pay to bear multisig method, fake multisig method. As you can see, this is a standard script of a one of three multisig. So you have one, you have three, and you have three public keys or hashes of the public key sandwiched between, and you have a check multisig opcode. So you can use this to store data. As we discussed earlier, you just fill these three public keys with arbitrary data that you want to store. You can add one genuine key in order to make it further spendable. But if you perform the if you perform calculations on what would be the value and stuff, it's not practical. Typically, people when they want to use this method, they just fill all the three keys with the data that they want to store. So this also bloats the UTXO set because it burns sats, and you cannot spend these UTXOs that you create further. And if you do some back of the envelope calculation, you can typically store 92 KB of data per pay to multisig transaction. So this is a lot higher than what you can do with this pay to fake public key hash method. So people have also used this method. So then comes op return. So having observed all these behaviors on chain, the core developers decided that there is no way for us to discourage or prevent or stop people from inserting data into the blockchain. So the consensus was that let's introduce an opcode, a clean way, so that people can store data. So this was introduced in 2014. So they introduced a new script sig type. So it's very simple. You put op return followed by the 80 byte data. So this can be so you create a transaction, you have an input, and you can have a series of outputs, and one of the outputs can be of this type. So one of the output scripts can be this, and the limitation is that only one output can be an op return output, and there cannot be more than one op return output, and the maximum data that you can put in an op return output is 80 bytes. With respect to the value field in an op return output, you can enter any sats. Means you don't have to lock those sats into that particular output, and you will not end up creating an invalid UTXO that just sits in the UTXO set, but it can't be spent anytime in the future. So you don't have to do that. When a node sees this output with this op return as a script pub key in it, it can very well discard it from its UTXO set. So these are the basic outlay of how an op return works, and why the developers thought that this is probably the cleanest way in which you can store data. Okay, then there is this pay to fake script hash method. So in a pay to script hash method, typically this is the standard script pub key. So you have op hash 60 followed by the 20 byte redeem scripts hash, and then op equal. So the plain vanilla way is to replace this 20 byte redeem script hash with the random byte that you want to spend, random data that you want to encode. This has all this. This has the same problem as your pay to fake public key hash method. Means you have to lock some sats, and it bloats the UTXO set. And it is also hard to detect because this 20 byte script hash can be anything. So your script can be anything, and there is no way to detect whether it is an arbitrary data or non-monetary data that you are hashing. So this method is also have been used, but there are some improvements that people have made to this method to make it much more effective. So that is called as the data drop method. So this method works in two steps. So it's a clever way of using the pay to script hash method. So what you do is that you have two stages. First, you have a setup stage, and then you have the data carrying spend stage. So in the setup stage, you typically use a short or small redeem script like this. So you have two drop functions followed by a public key and object sig. So use this redeem script. You hash 160 this redeem script and you will get a 20 byte redeem script hash. Then you construct the pay to script up key, so which is typically op hash 160 followed by the redeem scripts hash and then op equal. So it's nothing but the same the standard script up key of a pay to script hash. And then you spend some sats to it above the desk limit. You broadcast the transaction and the transaction gets mined. So this is the first step. Mind that there is no data that has been encoded so far. So it's just a staging or setup transaction. So next thing what you do is that you use the following. Next thing is that you use this transaction as the input, and you spend it to another output. So what you do is that you create another script sig with the signature and whatever data that you want to push into it, uh, followed by the whole redeem script. So this is the whole redeem script that we have put it in the first stage one transaction. So when the script executes it, this the when the script executes, so these opcodes will be at the bottom, and on top of this opcode, you will have this script sig. Uh, Now, when the script executes, this signature will check out or will match with this public key, and the script execution will pass. But where you are inserting the data is that instead of using some valid or redeem script that has some payment logic inside it, you are putting arbitrary data into this redeem script. So this is where the data gets into a transaction and becomes part of the blockchain. So when you perform this second transaction where you are spending from the first transaction, the data gets inserted into the blockchain and becomes part of the blockchain. So this is sort of a clever way. The advantage is that it doesn't create any bloat, or it doesn't contribute to the bloat of the UTXO set, because you are not creating any invalid transaction where the output goes and gets locked. And it has a higher payload, so you can put in like 1.5 KB of data per input, and you can put in like 90,000 or 90 KB of data per transaction. So this is the this is a lot more sophisticated way of inserting data into the blockchain. Uh, so these are all the legacy methods of inserting data into the blockchain. So data hash is also similar to the data drop, except that instead of using a public key, here you will be using a hash of the public key. So it is similar to this method. So there have been people have analyzed all these different methods that have been used, and there are many statistics or graphs as to say when which method was popular. And as time went on, some methods got dropped. They became unpopular because of the nature of their costliness or nature of the data insertion. So after Taproot, new doors have been opened. We have inscriptions. Inscriptions is a new way of putting data into it. They utilize the snor signature and tap leaf architecture to insert data into it. So all the we got to learn about these contexts because there was one question in the Stack Exchange, Bitcoin Stack Exchange, as to why some people are still using op return over inscriptions. So inscriptions are generally inscriptions are methods are methods that use the taproot architecture to store data into the blockchain. So one curious reader was asking why people are still using op return when inscriptions have emerged, which are a much more efficient way to store data. So the answer is the inscription is also a two-step data storage method, as we saw in the data drop method. So you have to have a staging transaction, and then you have to have a spending transaction where you actually insert the data. So there are protocols that don't want this two-step method of storing data. They want only a single they want to store data only through a single transaction. They are willing to pay the extra fees, but they want finality within one single transaction. So these kinds of protocols, data storage methods or protocols keep using op return. And also op return is used by other privacy preserving transaction spends such as paynims. So paynims is a method is similar to silent payments, where you can send Bitcoin to a recipient without him revealing his address publicly to you. So these kinds of protocols require op return, and that's why op return is still being used. Yeah, I'll pause for a minute.
Silent payments and paynims require op return to be used. Is that the case?
No. Silent payments don't require op return, but paynims require op returns.
Oh wow. Okay, I haven't like studied paynims at all. I don't know if it's outside of the purview, but why do they require op return? What benefit does op return give?
Yeah, paynims basically operate by, for example, in the protocol, you and I can create a NIM, and this NIM is stored in some shared centralized directory. So if I want to send you some transaction, so I can fetch your NIM from the directory, or you can send me your NIM through another communication means. And when I try to pay you, first I will send a notification transaction. That means I will send you a notification transaction, and you will send me back your address at the top level. I'm just explaining you at the top level. And you will generate a new address and send me back that new address, and the actual transaction will be done at the second transaction, where I will send you the actual BTC. So there is always a handshake or notification transaction that happens before the actual transaction goes through.
Okay, I think I understand it fair bit. And the centralized shared directory also does not need to know our name, does not need to know more than our name. Sorry.
No, the centralized directory is a convenience thing. So if I know you, I can always get your name directly from you. The problem is when I don't know you. So there are centralized servers that host different names, and people will voluntarily say that this is my name. So you can fetch my name, somebody else's name from that directory, and use it to send transactions. Okay. So we are nearing the 9 o'clock mark. We'll have a quick look at what reachable and non-reachable nodes are. So this is also we are exploring this because of a question that was asked in Stack Exchange, where somebody was asking, like he was setting up a node and his node was not visible in the public directories that contain a list of nodes. So why does it happen? Why does it happen? That is because whenever you set up a node, it can either be a reachable node or a non-reachable node. So reachable nodes are typically are called as listening nodes, while non-reachable nodes are non-listening nodes. So reachable nodes have opened up their ports to accept inbound connections, which means they serve many peers. So they propagate the blockchain to many peers. Non-reachable nodes limit their inbound connections or relay to only a set of trusted 8 to 10 outbound peers. They don't accept incoming connection from unknown or new peers. So non-reachable nodes typically don't help you in performing IBDs or bootstrapping you in help you in bootstrapping the blockchain. So it is only the reachable nodes that help in bootstrapping the blockchain. Also, the issue with non-reachable node is that they are not typically countable. You don't know how many nodes exist, how many nodes actually exist. So whatever estimates that we get saying that so many nodes, there are so many nodes running world over, they all fall into the reachable node category, and only the reachable nodes are countable. Typically, non-reachable nodes stay behind a tar address or an onion address. So there is no way for any node to publicly or statistically estimate how many non-reachable nodes are there. So whenever you see numbers touting that there are so many Bitcoin nodes in this country, so many Bitcoin nodes in that country. So you must remember that these are all reachable nodes. There may be more or multiple orders, more non-reachable nodes running. The problem with the reachable nodes is that you are typically exposing your IP. So, in order for your node to be popular or highly reachable, you should have a static IP, and it should open its port 833 to inbound connections. So this marks a huge red paint on your node. So you must be ready or sophisticated enough to assess threats and address network threats when you run a reachable node. So that's why typically when you do Umbrel or other default node implementations, you typically start with a non-reachable node, and you'll have to work your way around the settings in order to make it a reachable node.
What
So
Umbrel
yeah,
makes you run a non-reachable node by default.
yeah.
So I am giving all my information to Umbrel, but not the Bitcoin network for some reason.
You are not. I don't know what you mean by you are giving information to Umbrel.
Umbrel will know my node, right? They will know my IP. They will know
Uh,
basically what I do with
no,
my node.
no, not necessarily. Umbrel is just a operating system. You can download it and install it on any device you have, and you can run. I don't think they transfer data from your local Umbrel implementation to their own servers.
Okay, right. Fair, right. I think
Yeah,
Umbrel is not just an OS though, right? It
I think they might be doing that. I think there are trackers to track the performance. As in on the Umbrella instantiation, probably they track whether user is coming
yeah.
like
If you
maybe
buy, yeah,
30
if you
days,
buy a
that kind of.
Yeah, if you buy a box from them, all these things might be installed by default. But
Right.
always you can buy a Raspberry Pi and install Umbrella on it and run it on your own.
Right. What makes me most curious is that by default, a lot of people are buying Umbrel because they want to be running nodes, right? Because as plebs, they wouldn't have the
Yes.
sophistication to run it on a distinct hardware or Raspberry Pi, and they will end up being a non-reachable node and think that they are part of some public directory. And hey, I'm running a node. I think this is happening with a lot of people if they are, if they are non-reachable nodes.
I think Umbrel mining your data is orders of magnitude safer than you becoming a reachable node.
Okay.
So,
Bala, I think by default, umbrella nodes are reachable, right? It's only when you use IP Tor or you use some of these Tor services, then it becomes unreachable. Am I
no,
not
no.
right?
No, by default, all nodes are non-reachable. By non-reachable, it doesn't mean you don't accept any incoming connection. You limit your incoming connection to 8 to 10 peers, and this list of peers is like maintained and regulated by the core itself, by Bitcoin core itself. So there is a ranking mechanism inside your core, whereby some peers are ranked healthy, some peers are ranked unhealthy, and this list uh, is managed by core itself, and you connect to a select list of them. But when you run a reachable node, you don't limit. You are open, and whoever asks you for information through the P2P protocol and protocol structure, you will give them information.
Yeah, makes sense.
Yeah.
You can still do that, right? I mean,
Yeah,
you can
yeah,
always have more inbound connections. I haven't used
yeah,
Umbrel,
yeah.
by the
You
way.
can.
I have run a node on my laptop, and I found that relatively easy. It's actually easy. I don't know why people say that you want to be using Umbrel or like easy packaged solutions. I think it, of course, takes some technical expertise and savviness. So that's why it made me curious. Like you made a good point that it's orders of magnitude safer that Umbrel is mining your data than to become a reachable node, right?
Yeah, yeah, yeah,
Yeah, but
yeah.
I think most people are not running Umbrel because they want to be safe. They are running Umbrel because they run a node, is my understanding. That's the main reason.
Yeah, Umbrel is the most like popular instance or easy way of running a node, and that's why people are attracted towards it.
Right, right. Yep, yep.
Yeah, cool. The last item that we want to discuss today is different data filter configurations that is available with core itself. So core like in this debate, in this whole debate, people are like so focused on hating core and supporting knots that they actually don't know what is inside core itself. So core has like they have an extensive set of configs that you can do to filter at various levels. You can filter whatever you want at various levels. I agreed that Knots has implemented few advanced filtering options over on top what Core already gives. That I don't know whether people who are jumping into Knots even know what configuration options that Knots provides them on top of what Core does. They might always end up tweaking whatever configuration options that are available in Core. So I think people should have a look at what is available first in Core, and then get passionate about supporting Knots and stuff. So
I'm glad we don't have Delson right now here. Otherwise, it could have gone on for 1 hour now.
yeah, yeah, yeah. So Agile Core itself provides a lot of options. So you can go in your config, you can enable blocks only. If you put this blocks only in your config, it completely disables transaction relaying. So you will just receive blocks, you will verify the blocks, and you will not relay any transactions. So it's a very frugal way of running your node. It hogs very little memory of your node, So this is typically useful when you are like very selfish and you just want to protect your own privacy and your own transactions integrity. You can use this blocks only mode. Um, then you have this max mempool parameter. So this max mempool is set by default to 300 MB. So what this does is that it sets a limit on how much RAM memory that your node can use in order to store mempool data. So if you feel that at this moment the mempool is awash with a lot of data carrier transaction or inscription transaction, you can very well reduce this mempool transaction mempool limit. What happens is that if you reduce it, it generally doesn't prevent or prevent your node from relaying data carrying transaction. It just reduces the computational load on it. So you can do that with this configuration.
I'm
Then
sorry,
you have
I did not understand it, Bala. Would you mind explaining it again?
yeah. So when you set the max mempool parameter in your config, the default value that the core has is 300 MB, which means it can use 300 MB of your RAM to store and process mempool data.
But that should be like
Okay.
Mbps, right? What do you mean by RAM memory? That it's using it's not the hard disk or permanent storage,
No,
right?
mempools are dynamic data. See, mempool data doesn't go into your hard disk.
Right.
So mempool lives only on your RAM. So because transactions keep coming in, the list varies. You have to reorder the mempool. So it's all in random access memory only. So by limiting this max 300 MB, you can reduce it. Maybe say 100, 200, whatever you want. You can control the computational effort that your node expends.
Okay, makes sense. Yes.
Yeah, that is one setting. Then the third one is minimum relay fee. So you can set lower bound for transaction relays. So you can increase or decrease this minimum relay transaction fee. So what this does is that it doesn't your mempool doesn't populate any transactions below this fees. So they are not admitted into your mempool and they are not even related to your PS. You can use this setting also. Then the fourth one is data carrier filtering. So this is the one that you use to turn off op return data from your UTXO sets.
Yeah,
So
this is the point of contention right now, right? This one.
Yeah.
This feature.
Yeah.
Right.
Yeah. So when you set data carrier equals 0, it completely prevents relaying transactions that contain op return outputs. So whenever you find a transaction containing op return in its output, if you set it to 0, it just removes the transaction from your mempool and also your UTXO set. And you can play with this if you put data carrier equals n some number. What it does is that it prevents relaying transactions containing op returns of size greater than n. So you can set limits to the size of the data. So by default, the size of op returns is capped at 80 bytes. Still, if you don't want even that, you can vary it from 0 to some whatever number you want, between 0 and 80. That is one thing. Then again, we have this bar multisig filtering. As we saw in the types of or ways in which you can put data into blockchain, bar multisig is one method by which you can store data into the blockchain. So you can use this permit bar multisig equals 0. So that means bare multisigs will not be like looked at as a standard transaction by your node. So these are all the ways in which right now you can filter contents in your own node if you are running core. So Knots provides all these 5 methods. On top of that, Knots has a few other filtering techniques that you can use to further filter data. So I think now you can have some idea of what core offers, and then probably evaluate what Knots offers.
Yeah, makes sense. Why would I want to censor or filter only bare multi transaction? What is special about bare multisig?
Um, Nowadays, nobody uses bare multisig for a multisig. So, if you are using a multisig, most multisigs are paid to witness script hash type only.
Right,
Uh,
right,
so, if you find a bare multisig transaction coming across, that means either somebody has suddenly woken up after a coma or something, and they are trying to use use the network, or
right.
somebody is trying to store data. So these are all the two cases in which bare multisig can potentially be used nowadays.
Right. Got it. Got it.
Yeah, and it is most likely to be for data storage than some random dude waking up from a coma.
Right.
Yeah. Okay, that concludes today's session.
Thank you, guys. Good night.
Okay, thank you guys. Good night.